The Big Bang Theory stands as the leading explanation for the origins of the universe. It proposes that the universe began as an infinitely small, hot, and dense point approximately 13.8 billion years ago and has been expanding ever since. This theory encompasses a wide array of concepts from cosmology, astrophysics, and quantum mechanics, detailing the evolution of the universe from its earliest moments to its current state. Understanding the origins of the universe through the Big Bang Theory involves both observational evidence and theoretical models, which explain the processes that shaped everything from the formation of elementary particles to the creation of galaxies and stars. The Big Bang is not an explosion in space, but rather an expansion of space itself. According to the theory, at the very beginning, the universe was concentrated in an extremely small, hot, and dense state. This state is often referred to as a singularity, though modern physics suggests that the conditions at the very beginning may not exactly be a point in the traditional sense. This singularity marked the inception of the universe as we know it. The beginning of the universe can be described through several key moments. At time zero, all matter and energy were condensed into a singularity, a point where the laws of physics as we know them break down. This is the earliest period after the Big Bang, where quantum effects dominated. The four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, may have been unified in a single force. The universe expanded exponentially during this period, increasing in size by a factor of 10^26 in less than a second. This sudden expansion explains why the universe looks uniform and isotropic on large scales. The cosmic microwave background, CMB, is one of the most significant pieces of evidence for the Big Bang Theory. The CMB represents the remnants of radiation from the early universe, released about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. These photons have traveled through space ever since, offering a snapshot of the universe at that time. The discovery of the CMB by Arno Penzias and Robert Wilson in 1965 provided strong evidence for the Big Bang, confirming the idea that the universe had a hot and dense beginning. As the universe expanded and cooled, matter began to form. Initially, only fundamental particles like quarks, electrons, and neutrinos existed. As the universe continued to cool, quarks combined to form protons and neutrons. During the first few minutes, known as the primordial nucleosynthesis, these particles formed the first simple elements, primarily hydrogen and helium, with trace amounts of lithium and beryllium. As the universe continued to cool, atoms began to form during a period known as recombination. Photons decoupled from matter, and the universe became transparent to light for the first time, allowing radiation to travel freely. After the formation of the first atoms, the universe entered a period called the Dark Ages, which lasted for hundreds of millions of years. During this time, there were no stars or galaxies, and the universe was mostly dark, with only neutral hydrogen and helium gas. Eventually, small density fluctuations in the gas led to the formation of the first stars and galaxies. This period is known as the cosmic dawn and marks the beginning of the first light in the universe. The expansion of the universe led to the formation of large-scale structures such as galaxies, clusters, and superclusters. These structures are formed by the gravitational collapse of matter that was originally spread out in an almost homogeneous fashion. Small fluctuations in the density of matter provided the seeds for galaxies and stars to form. The first galaxies were small and irregular in shape. Over billions of years, these galaxies merged, grew in size, and began to form more organized structures. The process of star formation in these early galaxies led to the creation of heavy elements like carbon, oxygen, and iron through nuclear fusion in stellar cores, which were eventually spread throughout the universe by supernovae. A significant portion of the universe's mass and energy is invisible and does not emit light. This dark matter and dark energy have become crucial components in understanding the overall dynamics of the universe. Though it cannot be directly observed, dark matter has been inferred from its gravitational effects on galaxies and galaxy clusters. It is believed to make up about 27% of the universe's mass-energy content. Dark matter helps to explain the rotation rates of galaxies and the gravitational lensing effects seen in clusters. Dark energy is a mysterious form of energy that is driving the accelerated expansion of the universe. It is thought to make up about 68% of the universe's total energy density. The discovery of the accelerated expansion was made in the late 1990s through observations of distant supernovae. The ultimate fate of the universe is still a subject of active research. The future depends largely on the properties of dark energy and the rate of cosmic expansion. If the universe's expansion continues to accelerate, the most likely scenario is the Big Freeze, where the universe will become increasingly cold and desolate as stars burn out and galaxies drift apart. If the expansion of the universe slows down and reverses due to gravitational pull, the universe could eventually collapse back into a singularity. If dark energy continues to increase in strength, it could eventually tear apart galaxies, stars, planets, and even atoms, leading to the Big Rip. While the Big Bang theory is the dominant explanation for the origin of the universe, other theories have been proposed as alternatives or extensions, such as the multiverse theory, which suggests that our universe may be just one of many universes in a multiverse, each with different physical constants and laws. String theory proposes that the fundamental particles are not point-like, but rather tiny vibrating strings. This theory aims to unify all forces of nature, including gravity, into one framework. Cyclic models suggest that the universe undergoes infinite cycles of expansion and contraction, avoiding the need for a singular beginning. The Big Bang theory has dramatically changed our understanding of the universe, offering a coherent and testable explanation for its origin and evolution. Over the past century, scientific advances in observational astronomy, particularly the study of cosmic background radiation and the discovery of the expansion of the universe, have reinforced the theory. Despite the remaining mysteries surrounding dark matter, dark energy, and the ultimate fate of the universe, the Big Bang theory remains a cornerstone of modern cosmology, and its exploration continues to inspire new discoveries and ideas about the universe's vast history and future.